They process information from their environment, and they make decisions. So they act on that information. And so in this very general sense, I would like to discuss this fundamental question of how biological systems actually balance a very important trade-off between making decisions when you have to upon exposure to appropriate information and ignoring that information when you don't have to respond. So it's very similar to what we encounter in signal processing, I think, in terms of detail preservation and noise suppression. Those are sort of competing requirements. And so this is the overall theme of my talk today. So I would like to first make a somewhat general introduction to biological systems, just so that we are kind of more or less all talking about the same thing. So, biological systems are really complex dynamical systems. So if you look at a single cell, one cell, maybe it's a bacterial cell or a human cell, it is a large dynamical system of molecular interactions. So there's DNA and RNA and proteins and metabolites and many other kinds of biomolecules that are interacting in complex networks inside the cell. And these networks govern all cellular behaviors, essentially. Now, if we also go to the next level of organization, we can think of organisms as complex dynamical systems of cells. So, whether we're talking about the brain, which is a network of neurons, interconnected neurons, or an entire organism like an insect, there are many different cells that are communicating in very complex ways, physically and chemically, molecularly, over longer distances through diffusion. So the overall behavior of this complex systems is what we think of as the phenotype, right? This is what, for example, for the case of the brain, the phenotype would be thinking. The fact that you put all these neurons together gives us the ability to think and to have consciousness. So that's what I mean by phenotype. So this is not really that different from electrical engineering. In electrical engineering, we build circuits. And so the analogy of such a molecular network would be a circuit diagram. And the phenotype of the circuit is whatever the circuit does. It could be a radio or some other circuit, right? But if you look at the individual components, they're just resistors and transistors and capacitors. They just have individual operating characteristics, but you cannot infer the phenotype unless you put the system together. So same thing for biological systems. So systems biology is approaching biological systems as systems. So we take a systems approach. And as I mentioned, all cellular behaviors such as cell division, cell death, and differentiation, which is the execution of tissue-specific functions, and communication between cells, all of that is controlled by these circuits. And these circuits have been characterized in very deep ways. So this is actually a very old picture, but it already gives you an impression of how complex these circuits are. How many different connections, chemical connections, and even feedback exist in these circuits. So this is a signaling network. So these are typically protein-protein interaction networks that propagate the signal from outside the cell, from the environment, into the cell. And so that information is sensed by cell surface receptors, and then propagated downstream ultimately into the nucleus of the cell in mammalian cells, where genetic regulatory networks are actually doing all the work in controlling cellular behaviors. Okay, but let's not focus on that molecular biology. Let's zoom out a little bit and just make a quick comment about complex systems in general. Now, these systems are thermodynamically open systems, right? They are far from equilibrium. If they're in equilibrium, they will be dead. So a cell is constantly receiving input from its environment in the form of all sorts of chemicals and light and temperature and so on. And it is maintaining some kind of a constant or more or less steady state, even though it's far from equilibrium. The same thing is, you can think of our planet Earth. It's also an open system because there is constant flux of energy in the form of solar radiation, and that it is emitted back into space in the form of long wavelength radiation. And despite this, the average temperature on the planet is more or less constant. So, how does a biological system manage this trick of maintaining a stable state, but at the same time making decisions when it needs to make a decision and changing its state, sometimes drastically? So this is the fundamental trade-off that we come to now between stability and adaptability. So a biological system needs to be stable, obviously. But it cannot be too stable, because if it's too stable, it will be like a crystal. It will not be malleable to change. It's not flexible. At the same time, a biological system has to be adaptable. It has to respond to environmental signals, but it cannot be too responsive. Otherwise, it will be fragile. It will be like a chaotic system that responds to every little perturbation. And so, how can we quantify this trade-off mathematically? Well, we have tools from dynamical system theory, such as Lyapunov exponents, which allow us to quantify this dynamical stability. So let's turn to a prototype genetic network. This model class has been invented in the late 1960s by Stuart Kaufman and has become quite a popular model class of discrete nonlinear dynamical systems, mainly used as models of genetic regulatory networks. So, the system is as follows. Each gene is idealized to be a binary variable, 0 or 1, and the genes conspire to control another gene through some wiring diagram, through a circuit. And the way that they conspire to control another gene is through a Boolean function. So those genes are used as an input to a Boolean function. The Boolean function then determines the output of another gene. And how do you get dynamics? Well, the output of that gene that's determined by the function is determined at time t plus 1. So the gene gets updated at a ticking of a clock. And if you assume that all genes get updated at the same time, synchronously, the system will simply transition from one state to the next state according to the updates of the Boolean functions. Very simple. The mean connectivity of these Boolean networks is referred to as K. So this is simply the mean number of inputs for any given gene. Now in biological systems, I should say that this represents transcription factors. Transcription factors are proteins that can bind to the DNA of another gene and turn it on or turn it off. And often that is combinatorial, which means that there is more than one transcription factor that has to work together. And hence you get these Boolean rules. Sometimes they work together as an AND, sometimes they work together as an OR. And there could be other relationships as well that are more complex. Now, if we build these Boolean networks randomly, let's just say we assign them completely randomly, random Boolean functions and random wiring. So we can construct ensembles of Boolean networks. Now we have several parameters. One parameter is P. This is the bias of the Boolean network. So if we generate a truth table of a Boolean function by flipping a coin, P is the probability of the coin falling in heads. If P is equal to 0.5, we say that it's unbiased, and on average the Boolean functions have the same number of zeros and ones. But if it's away from 0.5, then you have more zeros or more ones in the Boolean truth tables. So, this, as a result, that goes back to 1986, which characterizes the dynamical behavior of these Boolean networks in terms of their ability to propagate small perturbations. So imagine the following scenario. Take a state of the Boolean network, right? So let's say you have n genes. So you have n bits in your state, okay? And suppose that I now alter one gene of that state. I switch it from 1 to 0 or from a 0 to a 1. I just flip a bit. Now, I've created another state with Hamming distance 1, right? So I've made a perturbation with Hamming distance 1. Now, if n is really large, that perturbation can be small, right? 1 over n. So we want to ask, what happens to the dynamics of the network after I make this perturbation? After I flip this one bit, will the two states, the unperturbed state and the perturbed state, will they drift apart or will they converge together? Okay? That's what this quantifies. So it turns out that for Boolean networks, there is actually a phase transition. And this is it. 2kp 1 minus p equals 1. This is the critical phase transition curve. So P is the bias, which I just showed you on the previous slide. And K, if you'll recall, is the average connectivity of the Boolean network. So how many inputs on average go into every gene. So just with those two parameters, using mean field approximations, you can show that this is the transition, the critical transition curve, whereby if you're above this curve, if you're above 1, you will be chaotic, and your single bit perturbations will drift apart. The trajectories will spread apart, and that's chaos. And if you're less than 1, the two trajectories will collapse together into the same state, and they will converge. So you have convergence in the state space. And when it's exactly equal to 1, you're on the border in a critical phase transition. Just like you have critical phase transitions if you're familiar with Ising models. Similar type of behavior here. Now, it turns out that this quantity is actually the Lyapunov exponent. And the way that you can show that is as follows. So the next two slides will be a little bit of mathematics just to make the definitions. So for a Boolean function, we can define the partial derivative of the Boolean function like this. It's addition modulo 2, or exclusive OR, between f0 and f1, where f0 and f1 corresponds to the Boolean function where you plug in 0 or 1 to the ith variable. So taking the partial derivative with respect to the ith variable, xi, amounts to this. Plugging a 0 to xi, then plugging a 1 in xi, and then asking, is the function different? Did the function change when I plug a 0 or a 1? When I flip the ith bit, what happens to the function? That's the derivative. Makes sense, right? It's the same as the continuous derivative, except it's binary. And now we can define the activity of the ith variable simply as the norm, or the expectation, with respect to the uniform distribution over the hypercube of this partial derivative. So, as you know, the hypercube has 2 to the n vertices, where every vertex is a state of the Boolean network with n bits. And so there are 2 to the n vertices, and this is the uniform distribution. You simply divide by 2 to the n, and you average. So, this is called the activity. So this basically quantifies how, if I flip the ith variable, how sensitive will be the function to that flip? On average, how many times will the function change if I flip the ith variable? For all the values of the other variables. And now, we can define the sensitivity of the function at vector x. So this is, vector x is one vertex on the cube. So it's a binary vector. The definition is the following. How many of the Hamming neighbors on the cube are different from the function value at vector x? So imagine that you're looking at vector x on the cube. You look at all the Hamming neighbors, there are n of them, right? You look at all the Hamming neighbors and you ask how many of them are different as the function value on those neighbors. And so you can write that as the sum of the indicator function of f of x exclusive OR the unit vector e sub I is not equal to f of x. So this is the unit vector that has 1 in the ith position. This simply means I flip the ith bit. If the function is not equal to f of x, then I count that as 1. So this simply counts the number of Hamming neighbors, okay, that are different from the value of f at x. And then we can take the average of this sensitivity across all the nodes on the cube, all the vertices on the cube. So I simply take expectation of this, and I can put expectation inside the summation. Expectation of the indicator function is simply the probability, because it's binary. And the probability that function f at the I Hamming neighbor is not equal to f of x is simply the activity, as I already defined on the previous slide, right here. Right here. So that means that the average sensitivity of the Boolean function is simply the sum of all of its activities of the I variables. Okay? So that's the background. Now, it turns out that this sensitivity is exactly the Lyapunov exponent. That exactly corresponds to this quantity right here. Except this is the mean field approximation when n goes to infinity in the thermodynamic limit. Okay? So, this is the Lyapunov exponent. So why is this important? It means that if you give me a Boolean network with Boolean functions and a wiring diagram and everything, I can tell you exactly what the Lyapunov exponent will be of that Boolean network. I can tell you if it will be chaotic, or ordered, or critical. Now, we can obviously tune these networks to undergo such a phase transition by tuning the connectivity, tuning the bias, and tuning some other things. I don't want to get into that. But basically, the point I'm making here is that we have a great toolbox for tuning Boolean networks to go through phase transitions. And there has been some early evidence that biological systems, that cells, are actually operating as what is popularly referred to as the edge of chaos. So biological systems are poised at a phase transition between an ordered and a disordered regime. And that is presumably what gives them their spectacular characteristics. And this also applies to the brain, and to bacterial colonies, and to ant foraging. There are many, many papers out there, ranging from ecosystems to neuroscience to molecular biology, showing that biological systems appear to be critical, poised at the critical phase transition. Okay, so, again, I don't want to get into this in the interest of time, but just to say that there are some, there have been some papers that given some early evidence that biological systems are critical. Now, I would like to get into information and how this pertains to information, which is the topic of this conference. So, how can we think about the dynamics of these systems in terms of information? Remember, I mentioned that the systems can either converge or diverge, right? So can we think of that in terms of information dynamics? Can we think of decreasing distances and expanding distances between state trajectories in terms of information? Okay, well, think of it this way. What happens if a system is ordered? If a system is ordered, there is convergence in the state space. So what happens? If you started in two different states, in the future you've converged, that means you forgot where you came from, right? You forgot that you started in those two different states because your state space converged. So if those two states were important for the biological system to discriminate something, you've lost that ability. You've lost information. Okay, now consider what happens if your system is chaotic. If your system is chaotic, you make a small little perturbation, could be noise, and now suddenly the system starts spreading apart, right? And now, again you lost information because you messed up your future, right? You're not able to propagate information forward in time because you keep flying off into, other parts of the state space where you're not supposed to go because you're so sensitive to perturbations. So in either case, information is lost. So this is sort of a kind of a intuitive way to see it. So, our basic tool here to quantify what happens to information dynamics in these systems is to use Kolmogorov complexity. So I'm not going to use Shannon. Probably most of you here in your work, in channel coding and other things, you're using Shannon's theory, right? Probabilities and so on. Is that right? Well, here we're going to use algorithmic information theory. We're not going to use probabilities here. We're going to use a binary, a string, x, that can be represented on a computer. It doesn't matter what that x is. It could be binary, it could be anything you want. And the Kolmogorov complexity is the length of the shortest computer program that can output this string. That's it. It doesn't matter what computer programming language you use. It can be just a universal Turing machine. But the point is that it's the smallest computer program that can generate that string. Unfortunately, that's not computable, because you cannot enumerate all computer programs. So this is how you should see it. It's the ultimate lossless compressor of X. So if you want X, you have to write a program that produces X, and the Kolmogorov complexity is the size of that smallest program. Therefore, it's the ultimate compression of X. Okay. So, just to give you intuition and why not probabilities, so what happens if I toss a bunch of coins and I show you something like this, okay? And I'll ask you, well, what's the probability of this outcome? Well, you could probably do some statistics and tell me something with some p-value. But suppose I give you this. What's the probability of this outcome? It's the same. Every coin is IID, Bernoulli, right? So this outcome is the same as that outcome, and yet you're never going to believe me if I told you that this was my coin flips. Never. Because it's too regular. And so this is the intuition for Kolmogorov complexity. This has a high Kolmogorov complexity because I can't compress it. The shortest program might be print, string. That's it. It's as long as the string. So it's kind of random. This one, I can do a really great compression. I can make a for loop that says print heads and tails 1,000,000 times, and that's a really, really compressed program. So that's the intuition of Kolmogorov complexity. So you need compression. Everything comes down to compression. Now, using this basic ingredient, the Kolmogorov complexity, it's possible to define a type of distance, an information distance, which is akin to mutual information in Shannon's model. However, it doesn't require any probabilities. And it uniquely specifies information distance without any parameters because it's only based on compression. I'm sorry, this thing is kind of trigger happy. Okay. So, the way to define it, and this is defined, I should have put a citation, I'm sorry. This is published in a set of really landmark papers in IEEE Information Theory and other journals by Paul Vitani and colleagues, and Ming Li and Chile Grassi and others from Amsterdam, mainly. And so this is quite a remarkable, I would say, development where you can implement the information distance using compressors. And you can use compressors like gzip or bzip, just regular lossless compressors. And the formula for the normalized compression distance, as they called it, which is an implementation of this universal information distance, amounts to the following. C of xy is the length, is the compressed size of strings x and y put together, concatenated. C of x is the compressed size of x, C of y is the compressed size of y, and here's the formula. Okay? So if two strings are equal, then the distance is 0. Okay. So now, what is so neat about this? The cool thing is that x and y can be anything you want. They could be a binary string, they could be a ternary string, they could be an encoding of a piece of music. It doesn't matter what the string is, because the semantics is irrelevant. The only thing that's relevant is compression to determine distances between two strings. So let's look at Boolean networks. Now remember, I told you that in Boolean networks we already have a good toolbox for knowing when the system is ordered or chaotic or critical. We already know that. So can we use this information dynamics idea using compression to analyze Boolean networks? So what do? Well, we take Boolean networks, which we know operate in different regimes, by tuning K, for example. So we can tune it to be in the ordered regime, which is blue. We can make it chaotic, which is green and purple. Or we can make it critical, which is red. Now, what am I showing here? I'm showing the normalized compression distance between any two states at time t, and on the y-axis, normalized compression distance between their successor states at time t plus 1. So this basically asks, if I have a certain information distance at time t, what happens to that distance at the next time point? Does that distance expand or does it contract in terms of information space? And if it expands, then we say that the system is chaotic. And if it contracts, it's ordered. And if it falls exactly on the line, then it's critical. And for Boolean networks, we see exactly this behavior. So this coincides with what we know theoretically from Boolean networks. We can also do scale-free Boolean networks, for example. This is where the wiring diagram is a scale-free graph, and you can control the scale-free parameter of the wiring, and also by doing that, you can tune the network to go from ordered to critical to chaotic regimes. And again, this corresponds to what has been known and published. Now, how about ternary networks? Ternary networks are networks where instead of 0 and 1, you have 3 values. Maybe -1, 0, and +1. Okay? So for ternary networks, it's still simple enough that you can analytically work out that the optimal connectivity is 1.5. Well, information dynamics shows that exactly. The optimal connectivity of 1.5 that gives you criticality falls exactly on the 45-degree line, which means the trajectories neither expand nor contract. Okay, so this all works out for models. Now, what if we took real data? What if we took cells and we measured their behavior over time, just like with Boolean networks, except we use real data from cells? So we took macrophages, which is an innate immune cell. This is a cell that exists in all of our tissues, and it protects us from invaders like bacteria and viruses. Okay? It's a very important cell type. And so this was an experiment, or actually many experiments, which quantified the behavior of macrophages after exposure to some stimuli that are essentially bacterial components. So you give some of those components to the macrophages, and then you take measurements at different points in time, just to see how they will start behaving. And you measure all of the genes in the genome, essentially. You do a genome-wide measurement, and you get a readout, just like you would in a Boolean network, of the states over time. So, if we discretize these data, either in the Boolean binary domain, or even in the ternary domain, and we repeat the same trick, where we apply the normalized compression distance to 2 states at time t, and then we look at their successor states, and we plot the distance at time t plus 1, we see that on average, it falls on the line. So there is evidence, again, maybe somewhat indirect, that biological systems are critical. So this supports a lot of other evidence that exists. And that holds no matter how you discretize your data, how you quantize your data. Interestingly, when you look at certain knockout cells, so these are cells where an important transcription factor, ATF3, has been knocked out. So this is a molecule that puts the brakes on the immune response. Basically, after you respond, you don't want your immune system to keep going and then eventually kill you. You want the immune system to stop. And so that's what this transcription factor does. If you knock it out, so if you have cells that are missing this transcription factor, basically the immune system doesn't know how to stop, and eventually it'll kill the animal, or the organism. So interestingly, when we look at experiments from those cells, the average behavior is a little bit above the 45-degree line, as you can see. So it shows that there is a tendency for chaotic behavior, meaning that it's very sensitive, which is exactly what happens. The immune system becomes very, very sensitive. Okay, so just very quickly, there's a lot of work showing that critical systems are in many ways optimal. For example, computation is so complex at the edge of chaos. And this goes back to the 1980s already, when people have been looking at it in terms of cellular automata and other dynamical systems. So one thing that we looked at a while ago, about 10 years ago, is something that we call Bayesian entropy. Now, a Boolean network or any complex dynamical systems has attractors, right? It has certain states that are steady states that the system will go to. And it can have multiple such steady states and multiple attractors. Now, all of the states that drain into a given attractor is called the basin of attraction. Okay, so you can imagine that the state space of the system is partitioned into basins of attraction, right? All of these states will flow into that attractor, and all of these states will flow into a different attractor, and all of the states will eventually go to some attractor. So you can think of that as associative memory. You start in some state, and you end up in some attractor state. So that's an associative memory. How much memory, can you quantify that memory? Sure. One way to do it is just to quantify the entropy of the basins. So if W sub rho is the relative size of the rho basin, if you partition the state space such that W sub rho's all add up to 1, and so that would be the entropy, the partitioning entropy of that basin of attraction, and we call it the basin entropy. So that is how much memory the system can store in its state space, in its dynamical state space. It's dynamical memory, right? Well, here's the punchline. When you tune systems such that when they're critical, that basin entropy, the memory, is maximized. And we can also show this theoretically in the limit, when n goes to infinity, that only critical systems maximize their memory, in the sense that it scales with system size. So if I increase n, if I increase the number of genes, my memory can also increase. Only if the system is critical. If the system is chaotic or ordered, all bets are off. It doesn't matter how large I make my system, my memory is going to be finite. It will not scale. And another work, briefly, that we showed with critical systems is that they maximize the relationships between structure and dynamics. In a sense, they are most diverse. Okay? So we applied, again, the normalized compression distance. However, we applied it to the structure and to the dynamics. Let me elaborate. The structure of the Boolean network is the wiring diagram and the Boolean functions. If I give you that, you know everything about the Boolean network. The wiring and the Boolean functions. So I can represent that as a string on a computer. Great. Now, I can run the Boolean network and I'll get a bunch of state trajectories. I'll get a big matrix of states. That's another vector or matrix, right? So I'm now in a position to use the normalized compression distance to look at information distances between structure of two networks and dynamics of two networks. You can put structure and dynamics in the same pot here, because the compressor doesn't care what it's compressing. So this is the really cool thing about this universal compression approach. So when we do this, again, we tune networks to be ordered or critical or chaotic, or to be randomly wired, or to be wired on a grid as in a cellular automaton. So you can do all of these things. And we find that when the networks are critical, which corresponds to this k equals 2, they are most diverse in terms of their dynamics. So on the y-axis, you have the normalized compression distance between dynamics of two networks, and on the x-axis, you have the normalized compression distance between the structure of two networks. So this shows that for the same differences in structure, you can get drastically different dynamics, only in the critical regime. And then finally, in another paper, we showed that we proposed a measure called set complexity, which is again based on normalized compression distance. And intuitively, this measure discounts sets with identical or nearly identical elements, or sets with random elements. So in a sense, you want the set complexity to be context dependent. You want it to depend on what else is in the set. And so, when we generate trajectories from Boolean networks, as I described in the previous slide, and we look at the set complexity of those trajectories, again we find that the complexity of those trajectories is maximized precisely when the Lyapunov exponent is 0, which is critical. Okay, so this is just some evidence. Okay, now I've talked to you about Boolean networks and ternary networks, and those are nice mathematical systems where you can play with them on the computer, and there's some nice theoretical tools that we at our disposal that we can use to analyze these systems. But what happens if I have other models? What if I have just a computer program, which sometimes is referred to as an executable model? Okay? And I'll show you an example of that. Or, alternatively, what if I have a system of nonlinear ordinary differential equations? This is a very popular approach in modeling biological systems. Just differential equations, which models the concentrations and the reaction kinetics inside the cell. So, what do I do with this? Can I use this information dynamics approach for this? So here's one example. This is an executable model that simulates interactions between two populations of T lymphocytes. So these are adaptive immune cells. Tregs, regulatory T helper cells, and naive T helper cells. Again, I don't want to get into the kind of the nitty-gritty of what these are, but just to say that these are cells that are arranged on a grid, two-dimensional grid. They have different states. They can be secreting some molecules. They could be moving. They could be giving birth, dividing to another cell. They could be dying. They could be differentiating. They could be secreting other molecules. They could be expressing some receptors that would make them able to read other molecules, to receive information from other cells, and so on. So this is essentially a computer program that just simulates the system. However, you can still look at the state dynamics, right? Because you can look at the state like this, and you can encode the entire system as some big vector. Right? Where are the states? What is the identity of the states? What are the concentrations of the molecules at each grid point? Right? I can essentially take a snapshot of the system. Okay, so if I do that, then I'm in a position now to apply the normalized compression distance again to those states. Right? Because the compressor, again, doesn't care what it's compressing. It doesn't matter how I represent my state of the system. As long as I have some state dynamics, I can look at the information distances between states. So, here's what we find. The black line is wild type, and the three color lines is when we knock out some of the genes in this model. So we essentially kind of disable one of the genes, and we ask what happens to the system when that gene is broken. And what this shows you is a multidimensional scaling representation of state trajectories computed from the normalized compression distance. So I computed the normalized compression distances, and then I got a big matrix of distances, and I gave that matrix of distances to multidimensional scaling, and it gave me this pretty three-dimensional picture, just so I can show it. So to show that the trajectories are different, that's the main point here. Okay? So the normalized compression distance is picking up the fact that these systems are different. They're now mutated or perturbed by knocking out these genes. And here is the similar maps as I showed you before, where on the x-axis we plot the normalized compression distance at time t, and on the y-axis we plot the normalized compression distance at time t plus 1. And these are density maps showing many, many ensembles of simulations from these systems, and we can see that the wild-type system mainly lies on the diagonal, mainly showing that it's critical, that this particular model of this biological system appears to be critically, behaving in a critical way. But if you knock out some of these important cytokines like IL-10 or interferon gamma and so on, so you do these knockouts, suddenly you have a lot more different behavior where you have either chaotic or ordered behavior in the dynamics of the system. So you can begin to look at these kinds of informational dynamics even from executable models. Models that are essentially not, quote, what we think of as mathematical, be it Boolean networks or differential equations. So you can still use this tool. It's a very, very general tool. Now, let's move to differential equations. So what happens if we have differential equations? We have a model of differential equations. This is a very common modeling approach in biological systems. So let's look at two quick examples. One is, both examples are from yeast, so from baker's yeast. And these models represent the response of the cell to carbon sources, to shifts in carbon sources. So you could give these cells galactose or oleate, which is a fatty acid, and these cells will turn on the necessary machinery to start metabolizing those carbon sources. Okay? And these are the networks, here and here. The oleate network consists of so-called feed-forward loops, and the galactose network consists of positive and negative feedback loops. So these are sort of things that people in biology like to talk about. Feedback loops and feed-forward loops and coherent feed-forward loops. I'm not sure it's as common in engineering, but basic idea is that some of these motifs of networks, little circuits, actually function either as amplifiers or as attenuators or and so on. And so biologists sort of think of it that way. When you look at the little circuits, what do they do? And so it's known already, there's already been done research on this, where that these kinds of networks are more sensitive and these kinds of networks are more stable. So we wanted to look at this from a different perspective. And here's a mathematical model, just so you get an idea that there are a bunch of differential equations which specify the messenger RNA levels, the protein levels, the kinetics of the oleate, which is the carbon source, the heterodimerization of activated transcription factors over here, and then the binding to the promoter of the DNA, and the transcription of the gene CDA4, which is here. Fractional interest. So there's a bunch of differential equations with a bunch of parameters, which, by the way, are experimentally determined. Okay, so this is a model that's been experimentally validated. So, again, let's look at the stability versus responsiveness trade-off. And as I mentioned, in signal processing, we often think of noise suppression versus detail preservation, right? We want to suppress, if we're doing like denoising of a signal or image, we want to suppress the noise, but we don't want to lose important details. We want to preserve those details. Of course, those are competing requirements. Who is to say what's noise and what's details, right? That's subjective. But biological systems are subjective, right? They act on their own behalf. They have to make a determination. What is noise? I'm going to ignore that. Or what is not noise? I'm going to act on that, right? So they have to make this decision. And all cells do this. If you take a simple bacterial cell, just E. coli, okay? This is the same cell that gives you a big stomach ache, and you get poisoned. So E. coli, how does it know where to swim? If you give it some sugar source, it will follow the sugar gradient. Well, it's implementing a Kalman filter. It's estimating the time derivative of the chemical signal. And it's just swimming up the gradient of the chemical signal. So it's implementing a Kalman filter. So it's estimating the internal state of a linear dynamical system with noise. That's what it's doing. Okay, so how does it know like when to respond and when not to respond? How do we analyze that if we have data? Okay, so here's our framework. This is my last part that I'll discuss in the next few minutes. This is based on time frequency. So here's the setup. Assume that you have some model sitting here in the middle, okay? Let me get that. You have a model. Now, we want to know its frequency selective behaviors, right? Sort of its Fourier behaviors. The problem is it's a nonlinear system. We cannot use convolution and standard textbook things that we all know and love, where we just know the impulse response of the linear system and we know everything. Here, we cannot decouple the output from the input, or the transfer function, so to speak, of the model from the input. The output depends on the input and on the system. Cannot be decoupled. So how do we analyze the frequency selective characteristics, like detail preservation or stability, of such systems? So here's an approach. We drive the system with many, many different ensembles of signals, different signals with noise, and we construct spectrograms. Or we can take short-time Fourier transform, or we can do other approaches that are more sophisticated. But basically you get time and frequency, standard stuff. Then you take the output of the system and you do the same thing. You take the spectrogram of the output. Now you have two spectrograms, input-output. You compare them. How do you compare them? Well, you extract certain features that tell you something about responsiveness or stability. And then you compare them. And then you can go back and you can vary the model parameters. You can change the model, you can tweak the model, and you can ask, how does that affect my stability or responsiveness? Okay. So just as an illustration, if you give a signal, here's the spectrogram of the signal, here's the response of the oleate system, here's the response of the galactose system, two different circuits. This is supposed to be more responsive, this is supposed to be more stable. Here's the spectrogram of that, here's the spectrogram of the galactose. You can see obviously more high frequencies here, right? So more sensitivity, more responsiveness. So how do we extract the relevant features from these spectrograms? Well, for stability, we simply look at the mean frequency. So we average over all time in each frequency band. Those are the f sub i's. And then we take the average. So just imagine that you have some distribution here over the frequencies. And we take the average of that distribution, and we'll call that mu f in, which is input. Then we do the same thing for the output. So we have mu input, mu output, and we take the ratio. So if a system is very stable, then its output mean will be lower, right? Right, so this, no, sorry. If it's very stable, then the numerator will be high and the denominator will be lower. Okay, so that's stability, and you can see already here quite clearly that the oleate model, in terms of the cumulative distribution over frequency bands, over all of these frequencies, it's more stable. Now, how do we look at responsiveness? Responsiveness is quantified by looking at the total variation of the spectrogram in each frequency band. So we simply add up xij plus 1 minus xij, absolute value, and that's the total variation going in each frequency band. And then we take that for the input and output, and we compute the symmetric Kullback-Leibler divergence between the total variation distributions of the input and output. So what's the intuition? The intuition is that if a system is responsive, meaning that it's responding to my inputs, then the total variation in each frequency band should be similar, and the Kullback-Leibler distance should be low. And so responsiveness is 1 over the Kullback-Leibler distance. And so if a system is responsive, it means it sort of tracks the input. The total variation in the input, it will be about the same as total variation in the output in each frequency band. And so that's how we define responsiveness. Now, it's important for me to point out that there's more than one way to define all of these things. This was just our idea, but you could define other ways to define stability and responsiveness using these spectrograms. But here's the, I guess, the interesting results. When we plot stability versus responsiveness, here's what we get for the galactose system. It's very responsive. Oops, sorry, not very stable. I'm sorry. Here we go. Now, the oleate model is much more stable. You see over here, you have more regions of stability and less responsiveness. But if you knock out some genes in the oleate model, you completely mess it up and you make it look like the galactose model again. It loses its stability. So by this knockout of this transcription factor, you basically cause the system to lose stability. And you can analyze this using these time frequency characteristics. And so remember, I told you that you can tune your model and recompute stability and responsiveness for each parameter tuning of your model. So here's the portraits that we get. The top is oleate, the bottom is galactose. Remember, oleate is more stable. It's kind of like a low-pass filter. And galactose is less stable and more responsive. So look at this. If you vary the strength of the negative feedback loop over here, and the strength of the positive feedback loop over here, those are just two parameters in the model that you can play with, okay? Well, guess what happens? If you recompute the stability and responsiveness, you get very different characteristics. And the wild type is the non-mutated or kind of what exists in nature. is, I know you cannot see it, there's a cross here, the white cross. It sits right here on this edge of this curve. So it's sitting in a very narrow region, almost like a Pareto optimal region of stability. That's the wild type. So if you tune your parameters just a little bit, you go away from this spot, you go over here, or you go over here, you lose stability. So it's interesting that it seems that evolution has tuned these systems precisely to be on this edge of stability. Same thing here with responsiveness, so right here. But if you look at the galactose, here's the wild type, right here. It's sitting in the middle of a sea of low stability. It's not stable at all. And if I fiddle with these parameters, this is logarithmic here, 100-fold. Not much happens. It still stays very not stable and quite responsive. Same thing over here. So the galactose network is much less sensitive to its values or its parameters than the oleate network, according to this analysis. And so this is how you can quantify these trade-offs. Okay, even for systems that are like models with differential equations. That's it. I'm done. I'd like to thank the people that did all this work. I'm not going to read their names, and some of these are collaborators. And thank you for your attention, and I'm happy to take any questions.
Classical information theory, as I said, indeed depends on the probability, characteristic probabilities. But it's quite a while that we have empiric mutual information, which means exactly the concept plays the major role. Like empiric mutual information is exactly the sum of the empiric entropies of the individual lines, the empiric entropy of the joint. And that we use, for example, for channel drawing. We have no idea what the channel is. And still it works exactly, it can be shown, like you knew the channel and did the best decoding. And that's what, for memory channel, what like Cesar Perner, 80s, for general channels, what by Jacobson himself, so we do have a quite rich information theory. Probability theory has nothing to do with probability because it's not there. For example, you have a painting of the same painter. Identify that. Paintings, Mona Lisa and other things, no probabilities. And still the algorithm work very well. Excellent asymptotic results and even not asymptotic, even for finding paintings. So we do have a rich theory protected.
Thank you for your comments. So this is empirical, so based on kind of statistical approaches to estimating information.
There is even not, it's like you compress the Mona Lisa. What's statistics of Mona Lisa? One picture. Still, you are sure to get the empiric entropy of that picture. And there is no algorithm that will ever be perfect. Not in general.
Right.
So that goes also to follow. For example, I have no idea what the channel is. It's not linear, it's like your example. It's not that you can break there, the frequency concept. Still, I have a system, here is the received signal output, here are possible inputs, I compute empirical mutual information, then all inputs, choose the best. Not only that I'm not sure, for example, that it gives good performance, it gives the same performance had you known exactly the characteristics of the channel, what it does, and not only in terms of limits like capacity, but the whole error exponent. Not the whole, but rather the noise. The order is known with the critical. So we do have rich theory. That has nothing to do with probability.
Thank you. I'd like to talk to you afterwards. Thank you for that.
Any other questions?
If not, let's thank the speaker. Thank you.